That's kind of funny. Alright, what's up guys? This is going to be, I think this is your first video lecture. First of all, I want to make sure it's still lined up. Yeah, that's good stuff. Alright, first video lecture, we are jumping into chapter 10. This is this is kind of a basic intro to calculus. We're kind of going to summarize a lot of what calculus is about in 2 days. And normally, calculus is really split up into two halves, with the first one being a derivative and the second half being an integral. And usually we talk about derivatives first. Next year when you're taking calculus, a lot of that first semester is going to be devoted to derivatives, and the second semester will be devoted to integrals. We're going to work backwards because this is the integral half of it. It's a little bit simpler to understand and see. It makes a lot more common sense. So we're going to do this first, since I'm not with you guys today. Hopefully it's easier for you to understand this via this video lecture versus the 10.1 stuff on derivatives. So we're going to start out talking about integrals. It's a really common sense idea. Once we get to it, it's going to make a lot of sense. It's not a big deal. I'm going to start with probably the easiest question I've asked you all year. So it's going to be a nice, easy way to start. So we're going to cruise through a few examples. The first example, I'm going to ask you a really simple question. If I drive a car at 40 miles an hour and I'm driving for 5 hours, how far have I driven? That's the question. So let's start with that one. If I drive 40 miles an hour for 5 hours, how far do I drive? Okay, so this is a really basic question. It's obvious. If we're driving for 40 miles an hour and we multiply by 5 hours, we get 200 miles. 200 miles. And before I go on with this, a quick note is units. When I'm multiplying miles per hour times hours, it's like those units cancel out. The hours cancel out, and I'm left with the units on my answer. So if I'm multiplying miles per hour times hour, I know my answer is going to be in miles. So if I'm multiplying, let's see, miles per gallon. Like if I say side note, you don't have to write this down. If I let's see, if I get 30 miles per gallon of gas and I use 8 gallons of gas, that's going to equal 240 miles, because the gallons cancel out. I'm left with miles, and that's the units on my answer. All right. Anyway, moving on. There's another way to view this very simple problem, and this is going to blow your mind. Let's pretend. Let's graph. I'm going to view 40 as a function, as my velocity function. It is my velocity, so I'm going to call my velocity, I'm going to write it like this. My velocity function in terms of t is just a constant function at 40. Let's graph that. So I'm just going to sketch a graph here. I'm going to use t for my x-axis. I'm going to use v, my velocity is my y-axis. And to graph that, just to sketch it real quick, I'm just going to draw a horizontal line at 40. This is v of t. Alright, if I'm traveling for 5 hours, I'm going to go up to 5 on my time axis. And if I go up and meet my graph, I create this rectangle. My question is, what's the area of that rectangle? That's pretty straightforward stuff. The area of that rectangle is just 5 times 40, or 40 times 5, which ends up being my distance traveled. So that's a another way to think about this problem. The conclusion I want to take from that is when I find the area underneath any velocity graph, it's going to give me the distance traveled. And it might be a constant function. In our next few examples, they're not going to be constant functions, but we're going to use the same idea, this area underneath the velocity curve. So let's write that conclusion. The area underneath a velocity graph is the distance traveled. I'm just going to say under B of t is the distance traveled. That's an extremely profound statement. We've never thought about distance traveled as an area. We've always just thought of it as in common sense terms as your speed times the time is going to give you how far you travel. But really what you're doing is you're finding the area of some shape when you're doing that calculation. It's like you're finding the speed is the height and the time is your length or your width of a rectangle or some shape. That's going to give you the distance traveled. So my extension of this is to say, alright, what if my velocity function is not constant? Let's say I'm starting at 40 miles an hour, but I'm increasing by 5 miles per hour every hour. So my function is just going to look like that. I'm going to start at 40 miles an hour, and my slope's going to be 5 because I'm increasing by 5 miles an hour every hour. So now, how far do I drive in 5 hours? And I want you to, it doesn't sound like that complicated of a problem. If I start at 40 miles an hour and I increase my speed by 5 miles an hour every hour and I travel for 5 hours, it seems like a pretty simple setup, a pretty simple scenario. But think about how I could possibly determine the distance that I've traveled. It's not easy. It's like my speed is continually increasing so that it increases by 5 miles an hour every hour, but it's continually increasing in that whole period of time. It'd be really difficult to find how far I've traveled. It's like I'm constantly accelerating. So it's not as easy as just finding the area of that rectangle. But we're going to use this same idea, this area under the curve. So let's sketch that graph real quick. So that starts at 40. There's 40. And it increases at a steady rate. So I'm just going to sketch it like that. I don't know if that's exact. It's just a sketch. And I'm going out, there's t, v of t, I'm going out to 5. Draw a line up. So again, but my distance traveled, the area here is going to equal the distance traveled. And now all of a sudden this is a simple problem. Because all we're going to do is I'm going to split this up into a rectangle and a triangle. We're just going to find the area of the rectangle and the triangle. So it's going to be equal to the area of the rectangle plus the area of the triangle. The area of the rectangle is easy. It's just 5 by 40. And then the area of the triangle is going to be 1/2 base times height. 1/2 base times height. The base is, we'll say the base is 5. But our height, we don't know. What I need to find here is the height of the function at that point. That's just the value of this function at 5. So let's just quickly find v at 5. So 40 plus 5 times 5, that's 65. So actually I end up going 65 miles an hour after 5 hours, which kind of makes sense. And so my question is, what's this distance here? Well, that's just going to be 25, the distance from 40 to 65. Alright, so this is 200. This is 125. Half of that is 62.5, I believe. That's awesome. I hate to sound like a dork, but we just solved a fairly complicated problem, turned it into this area problem, and it became a very simple problem. This is a simple application of calculus. Notation. Alright, so here's what we just did. The area under a curve under a function is an integral. That's what an integral is. That's all it is. It's just the area underneath the function. And here's what we use to denote an integral. And maybe you've seen this before in math books around. You've seen this symbol. But if I want to denote this area, I'm going to use the integral notation. It's kind of a curvy, elongated S. And my limits for time go, the lower limit's here, the upper limit's here. So it's going from 0 to 5. And then the function that I found the area underneath, which was 40 plus 5t, goes there. And then we add this notation, it looks like dt. This just tells me the variable that we're using, which is obvious, but it's just part of the notation. This is equal to 265.5. Alright, so this complicated looking thing just means the area under plus 5t from 0 to 5. That's all it means. That's integral notation. That's awesome. Alright? Alright, last example. Alright, now this is much different. This is much different. Because when I sketch this graph, so my question again is, how far did I travel over 5 hours? When I sketch this graph, start at 10, and it's a parabola. Draw like that, out to 5. It's good. This is much more complicated. So again, the area underneath, this is t squared plus 10. The area underneath, the area in here is going to be my distance traveled. But we can't use geometry to evaluate this exactly. Alright, we cannot break it up into a rectangle and a triangle because it's curved. Alright? So the best we can do here is to estimate it, to approximate it. And we're going to use what's called the left Riemann 2 ends sum. Okay, it's called LRAM. And here's what that is. Actually, before I explain what it is, I can. Okay, I'm going to break this up into 5 subintervals every hour. So I'm going to go 1, 2, 3, 4, and 5. I'll let you do that. And a left Riemann sum just says, in this interval, from 0 to 1, I'm going to go to the left part of it at 0, go up to the graph, hit the graph, and then make a rectangle. Okay? From 1 to 2, I'm going to go to, now the left part of it is at 1, I'm going to go up, hit the graph, go over, and then back down. At 2, I'm going to go up, hit the graph, and back down. From 3 to 4, I'm going to go to 3. I'm going to go up, hit the graph, make a rectangle. And then the last one, I'm going to go up to 4, make a rectangle. And I've got 5 rectangles. So let me review how I made that. In each interval, the height of the rectangle is determined by the value of the function at the left part, the left end of that interval. So if it's from 2 to 3, I went to the left part, I went to 2, went up to the graph, and made a rectangle. So what we're going to do to estimate it, we're just going to add up the areas of all these rectangles. So what that means is our integral from 0 to 5 of t squared plus 10 dt. So remember, all this means is the area under the curve. It's going to be approximately equal to the sum of the areas of the rectangles. So our approximation, we're just going to add up the areas of 5 rectangles. Alright? So our first rectangle, the width is 1, and the height is 10. The second rectangle, the width is 1, the height, I don't know the height. Alright, let's do something real quick. Let's make a table. T goes 0, 1, 3, 4, and 5. So let's go through and find the height of the function at each of those sub-intervals. So at 0, it starts at 10. At 1, 1 squared plus 10 is 11. 2 squared plus 10, that's 14. 3 squared plus 10 is 19. 4 squared is 26, and that will be 35. Okay, so what's my height at 1? What is that height? It's 11. The width of this next rectangle is 1. So the width, and then the height at 2 is 14. Length times height, width times height. Now notice, first of all, notice that I never used this last height because I never made a triangle with that height, because I was always using the left ends of each interval for the height, so I never used that last height. All right, so when I add all these up, it equals 105. 79, I'm sorry. If you add these up, you get 79 miles. So that's my approximation. So this area is 10, 11, 14, 19, and 26. I add them up, I get my estimation. Alright. If there's a left Riemann sum, there's a right Riemann sum. So let's do that. going to sketch my graph there. A right Riemann sum. This is R RAM. I'm going to sketch my graph again. T, V of t, t squared plus 10. Alright, let's break this up into 5 subintervals again. I'll use green. I'll use red. 1, 2, 3, 4, 5. Alright, the right Riemann sum. I hope you can predict what I'm about to do. All of my heights are going to be determined by the right side of each interval. So from 0 to 1, I'm going to go to 1 now and go over. Different color. Go over. From 1 to 2, I'm going to go to the right side. Make my rectangle. The right side, make my rectangle. And notice the height is always determined when I hit. When I hit it, then I go over. And then this one is a big one. Alright. So we can estimate these now. So my integral from 0 to 5 of t squared plus 10 dt is going to approximately be, so 1 times, now the right height is at 11, not 10, it's at 11. So we're starting with this one right there. We're not going to use 10. 14, 19, 26, 35. And this time I do use this last height because my last rectangle is determined by that height. It goes all the way up to 35. Okay? And when I just add those together, I get 105 miles. Okay, we need to compare these. It's a very obvious comparison. My question is this an overestimate or an underestimate? It's a pretty easy question to ask because obviously these triangles are all above the graph. So really, all of this space above is the overestimate. So this is an overestimate. Overestimate. If I go up to the top here, the first one, is this an overestimate or an underestimate? Well, all of this space is not being measured. It's an underestimate. And you can see there's a lot of space being left out here. My question is, how can I come up with a better estimate? How can I come up with a more accurate estimate of my distance traveled? Somebody? Blurt it out. Yes, you are correct. You are correct. The average. Our best estimate is when we average the LRAM and the RRAM. Is it 79? Yeah. And we get 92 miles. Okay, that's pretty good. When I do this, there is a way to calculate this exactly on the calculator, which you're going to learn next year. But the answer is actually 91.67, and that's pretty darn tootin' close. Alright? That's really close. So this is a pretty crude, almost primitive way to estimate this. We just broke it up, like it's almost clumsy. We broke this up into 5 rectangles. Our estimate wasn't even close. But when we combine the left and the right Riemann sum, we actually end up getting a really exact, a precise, a pretty close answer. Oh my gosh, we just calculated, if my speed increases like that, continually, we actually came up with, we answered a pretty tough question there. This is calculus. I love it. I love it. Alright. That is it. Peace.